Good evening, everybody. Hope you're doing well on this Saturday night. Keegan here from Curious Engineering, and tonight we are going to be going over Lab 2 Part 2 from Altera. So, in the previous video, I mentioned that we're going to be introduced to some new logic elements. We're going to talk about, eventually in this lab series, ripple carry adders, full adders, and in tonight we're going to talk about comparators. We're going to talk about data flow modeling and what's meant by the term register transfer level. And then we're also going to be talking about some switch case statements and what do those things represent, or how can you use those to your advantage. But before we get there, let's talk about our high-level purpose for this lab. What it's asking us to do is use 4 switches as opposed to our previous 8, and depending on the binary combination, we want to output those numbers to hex 1 and hex 0. A 4-bit number, as we know, can output anything from a 0 to a 15, so let's make sure we do that. And also in the previous lab, I mentioned we had these don't care conditions. So you might be saying, well, let's just use those don't care conditions for this lab. Well, you have a few problems by doing that. How do you control the most significant and the least significant bits, going to each hex? So okay, we got to account for that. And the other problem is we didn't even consider those in our decoder design, our 7-segment decoder design. We only coded that to output 0 through 9. So instead of going back and redoing that whole thing, let's just use what we've already designed and then hook things up a slightly different way, right? So Altera provides us a schematic to get us up and going. This is our V is being represented by our switches, our 4-bit switches. And throughout this lab and in the code, I'll use the same variables just to stay consistent with this schematic. So let's break this down a little bit. So the V switch inputs go right to the 0th position on the mux, and then we can see also that the 1 position on the mux is being represented by the output of circuit A. So I'll talk about why we need circuit A. And then we also see that what's controlling the mux is the output of the comparator, or Z. The Z also controls the mux, but it's gonna, whatever that value is, gonna be eventually put out on hex number 1. So if we look at the comparator, it's basically just saying, hey, is the value greater than 9? If it's not, then Z is going to output a 0, and then 0 will be displayed on the hex, and then also the switches will be selected, whatever combination that is, and it's going to be outputted or output on the hex number 0. So it's just be 0 through 9, which is exactly what we want it to do. The problem comes in when you get 10 through 15, right? So if the value is greater than 9, Z is going to be a 1, and we're going to consider the output of circuit A and not consider what the switches currently are. So a little bit strange there. So the Z is going to put a 1 there, which is what we want, but then circuit A is going to dictate what's being presented on hex 0. So, and this goes back to the question that we had of how do you control which goes to or what numbers go to what hex. So the easy way to break this down is say, okay, let's say, okay, what's our most significant digit? And in hex 1 is going to be that. So if it's 0 through 9, it's going to be a 0. When it's 10 through 15, we want that to be a 1. So it only has to be a 0 or a 1. Great. Hex 0 has a different problem. It goes from 0 to 9, and then it goes back to 0, and then it stops at 5. So we have to create some circuitry to make sure that this will indeed be true. And you might be asking, how do we do that? So we've broken it up into, okay, we want hex 1 to be something, we want hex 0 to be another thing. So if we focus on 10 through 15, 10, 11, 12, 13, 14, 15, if we look at that original binary switch combination, this should be, I'm going to say V, sorry. If we want to take a look at V, and then we want to see how do we turn it into, sorry, I should have done that before. Anyways, how do we turn that into A? And if we look at, how do you go from a 9 to a 0? Well, let's just compare what those binary values are. We know a 0 is just going to be represented by these 4-bit binary numbers, and then you do the same for 1, 2, 3, and 4, and 5. So that's what we have here. So we need to turn what was everyone on switches into this now. So we need to transform it. A great way to do that is let's just use what we've already known. Like we know AND gates, we know NOT gates, OR gates. So let's use those to our advantage and create that circuit A. What is that circuit A? So that's what we're going to do here. So what I've done in the next slide is we're breaking up all of those two combinations. We're breaking it into breaking up into columns, into our most significant down to our least significant bits. So let's take a look at when we have the most significant bits, bit number 3. Compare that to what it was before versus what it should be now. It's always a 1 and now it's always 0. So a great tool to use right there is an inverter. So we're just going to invert the input to give us our output on the 3rd bit position. I'm going to skip bit number 2. That's a little bit, I'll talk about that one a little bit. But if we look at bit number 1, that also is just inverted, right? What was a 1 is now a 0, and what is a 0 is now a 1. So we're just going to invert that one also. Perfect, which is what you see here. Now if we look at the least significant bit column, those are the same, so we don't have to do anything to it. Fantastic. The second one, we have to say, okay, how do we only get a 1 here and a 1 here? And if you kind of think about, well, I have AND gates, OR gates, NOT gates. We can't just use a NOT gate here. But if you see here, if you AND together the second and the first bit columns, you'll get this result here, right? Because you go 0 times 1 is going to be 0. Or sorry, 0 and 1 is going to be 0. It's going to be the same thing here. Oh, it's another 0. Yep, and oh, here we go. We got 1 and 1 is going to create our 1. 1 and 1 is going to create our 1. So take a little second to stare at that and try and convince yourself that that's true. But that is exactly what we want to create this output of circuit A. So we've created circuit A with 2 NOT gates and an AND gate. So bam, it's going to do exactly what we need to do. It's going to transfer a 10 into a 0 and an 11 into a 1. So it's going to do that exactly for us. So fantastic. So we've gone over this. We've created what we need to for circuit A. Now, before we talk about what a comparator is, let's talk about the idea of data flow modeling. So a lot of things that we've done in the past have been focusing on those gate levels, the AND gates, the NOT gates, the OR gates. Those, it's great, and don't get me wrong, I love like going down in the gate level and designing something to do exactly what you want it to do. It's very, it's very rewarding. So, but when you start doing bigger designs, you get into this problem of like, well, if I change something or if I made an error, I have to go back and change a lot of different things. It's not very efficient or effective. So what we want to do is like focus on the high level things and then let the logic synthesis tools that Altera has created, let them, let the tool lay out like exactly all the different gates for us, and it'll probably do it more efficiently, honestly. So this is going to the data flow modeling is a higher level of abstraction. We're saying I want to focus on, I'm going to use shorter, more concise statements, and then it's going to represent a lot of different things actually in the hardware for us. So that is what we mean by data flow modeling. It's essentially just a higher level of abstraction. So if you're a software person watching this, this is probably what you're saying. You're probably saying, ha ha ha, software or abstraction at the hardware level. Great joke, Keegan. But if you're thinking from a physical layout person's perspective, they're also saying like, I can't believe you're being so, treating this so freely as with hardware. You should be careful. But it's all about the idea of perception and like using what we have at our disposal to do what we need to. And data flow modeling is leveraging the power of those synthesis tools and allowing us to focus on the ideas or kind of like what we need to do, the timing and those issues. So what we've kind of already been using some data flow modeling. You see, we've been using the assign statements a lot. Haven't really used delay, but that's kind of a data flow thing. Logical operators, we've also been kind of using those. So all along we've kind of been doing some data flow modeling. And what I want to talk about is this conditional operator. Excuse me, sorry. For the comparator, that is going to be we're going to use the conditional operator. So the conditional operator is just a question mark. So how this statement works is you say, hey, test this Boolean combination. if that combination is true, I want you to do these things, and if it's false, I want you to do these things. And it's just you use the colon separator to separate the true from false, and then we always got to make sure we have our terminating semicolon. So it's great for switch control, and then we can create what we want. We want to create our comparators. We can create our multiplexers, if else, etc. If you find yourself needing to use these things, conditional operator might be a great thing. So I have just a little example here. Oh, my head's not in the way. Perfect. Okay, so for a 4-to-1 mux, if you were to use exclusively gates, this is everything you would need in code to create that. With the conditional operator in Dataflow modeling, you can simply use this conditional expression, and this will exactly create all of this. So, and here's this symbol for that. But let's take a look at that. So you're saying, hey, I have my output, which is my what we want. I have my 4 different inputs, and then I have my controlling selects, my 2 controlling selects. So I'm gonna say, hey, all right. So the output of out depends on this conditional statement, and we're doing conditional statements within a conditional statement, but it will work out very smoothly. So let's take an example. So S1, if that is 0, what is S1? Is S1 0 or 1? If it's a 0, we don't even consider this one. We jump to this section here. Okay, so we know it's false. So now we look at switch 0. So switch 0, is that true or false? If it's false, then we have alright, S1 is 0, S0 is 0, so it's going to be IO. Is that true? So if S0 is not true, it's perfect. We got our IO. But if S0 is true, we have I1, so that's perfect. It's what we want. And then if switch 1 is a 1, then we don't consider this combination. We just look at this combination. So you get the idea. So it's a great tool. Feel free to use it. I would get comfortable with using it because it'd be something you want to use going forward. So awesome. So how do we represent our comparator in code? I will pull up this, and I'm going to pull this up too, just to give me a sec. Okay. So let's take a look at our comparator, since we've kind of looked at high level what we want. So our comparator, where is it? Here we go. Okay, so our comparator, we're going to use that conditional statement, conditional operator, I should say. So what I've done for this module, it's pretty straightforward. I'm calling it comparator, and I want it to have these 2 parameters. Those parameters, the compare in, I'm saying, is a 4-bit bus, a 4-bit number, and we want it to output a true or false. That's going to be our Z, essentially, right? So you're saying, hey, what is Z? And you say, compare the input. Is that greater than this thing that we have here? So what is this? That's saying, like, hey, create a 4-bit binary. That's the symbol for bit, and then we use a B for binary. And then 9 is 1001, right? Okay, so is the input greater than 9? If it is, we're going to say the output, the compare out, is going to be a 1-bit binary 1. If that's not true, it's going to be a 1-bit binary 0. Perfect. That's all a comparator is. That's we're just leveraging the power of the conditional operator to create that logic that we want. So awesome. So I've talked about, let me just review my notes here. So okay, so we've gone over high level what we want to do. We've gone over the schematic. We've gone over kind of some conceptual things, and then we want to talk about the actual design. So let's put this design into use. So as always, let's create our project. Oh dear. Okay. I'm going to delete that. Actually, no. Lab 2 part 2. Okay. Creating a new folder here. I'm going to call it Lab 2 part 2. Okay, it's an empty project as always. What is our component? Don't know why I haven't been copy and pasting it before. Okay. So again, just consult this number on your chip if you are looking for exactly what device we want to target. So this is the DE1 SoC for me. We're not going to use any specific tools, so we're just going to say none to all of those. We're going to review what we have, and then we're going to say, good, create our project. And it's going to do it for us here, maybe. Okay, let's take a look at our files. We want to input our code, so let's say, hey, let's do new file. We want it to be a Verilog file. Okay, I have the design already, if I can click. Okay, awesome. So let's take a look at this code a little bit more. So we have our top level module, I should say, and we're going to use our switches as we know. LEDs is just, it's kind of aesthetics, but so we know what bits are what switches on and what switches off. Obviously our hexes. So we have those reserved primitives created here. Those are our ultimate inputs and our ultimate outputs. Within that, we're going to need some wires to hook up everything. As we saw in this design, we're going to need some wires in between circuit A. We're going to need some wires to the output from the output of mux, and then we need the wires ultimately to our hexes. So we are going to create a 4-bit bus for our V. We're going to create a 4-bit bus for our A and also our mux out. We're going to create 7-bit buses for our hexes because it's a 7-segment display, and then our Z we saw is only going to be a 1-bit binary, so we don't even need to say if it's a 0th bit. So, anyways, okay, what we're doing here, you know what, I'm gonna use this one because it's more zoomed in for you. Okay, so we're saying, hey, whatever switch combinations we have, assign that to V. Perfect. Our switches, whatever is activated, we want that LED to be on. And then the wires, those 7-bit wires that we created, connect those, whatever those values are, to our hexes, and that is being represented by the output of these. This should be a 7-segment display, these two. So whatever's being output by our 7-segment display, send those to the hexes. Okay, so now we've come to our instantiation portion. So instantiation is basically just a function, right? I've created a comparator module. I've created a circuit A module. We've reviewed both of these already. We have a mux 4-bit 2-to-1 mux, and then we have our 7 segments of that. So let's take a look at. I've already talked about those. Yeah, circuit. Oh, okay. So yeah, I talked. We saw how we want to design it with symbols and everything, but how do we represent circuit A in code? So we've created our module. I've just titled it circuit A, and then it has 2 parameters. It has a circuit in parameter and circuit out parameter. The circuit in is obviously an input, and it's 4-bit wide. We have an output parameter. It's also 4-bit wide, and we are just creating this essentially in code. Okay, so for our most significant bit, just invert it. Awesome. For our second bit, right, that was the special one, it needs to be ANDed with the first bit, and then our first bit, we just want to invert that one also, and our last one we saw we don't want to do anything with it, so just assign it the output to the input. Alright, we just want it to be wire to wire. Awesome. Okay. You know what? I think this is already a longer video. I'm not going to talk about switch case statements. I want to make sure we just see what this design looks like in code. Okay, so let's finish our design. Obviously, we have to do our pin planning. As I mentioned, it's always a good thing to have your typical commands already saved somewhere for all your switches, LEDs, and hexes that we're going to use. So it's just an efficient way to do that. I can't exactly remember which video I really went over where to find those. I think it's probably like lab 1, maybe part 2 and 4. But I'll go back to those videos. I go step by step how to find these things multiple times, so it's going to save you a ton of time from having to enter them directly. So okay, as always, I'm going to fast forward for you so that we. Oh, I have to save it. So 1 sec. I'm going to fast forward for you while it's compiling, so you don't have to watch it. And now I'm ready to compile. Awesome. Compile. Okay, and we're back, and everything has finished. It's compiled, and we have no error messages. Fantastic. It's always a good feeling. And let's go ahead and program this and see what it looks like on the board. Make sure it's behaving like we want it to. My hardware is not on, so let me turn that on. Okay. Okay, so let's choose that one. Yep, that's the one we want. Okay. Close. Okay, auto detect it. Choose our target device chipset. Hit OK. And then let's add our file, our output file as per normal. So go to your output files and your .sof file. Excuse me. Okay, let's open it. There's going to be an excessive one as usual. Let's delete it. Only want our one, and then if everything looks good, we'll see our 100% on our progress. And then now let's take a look at what we're trying to output. You'll see a zoomed in version of it on the upper, what is that, upper left portion of your screen. Sorry, this is my right. Okay, so let's just test one. So can we? Yep, we got one. Okay, let's test two. Awesome. So let's test 9. Okay, so we got a 9. And now the moment of truth. If we test 10, we should see it output correctly, which we do. Awesome, we feel good. So let's max it out. Let's go to 15. It shows 15. Awesome. Back to 0. So it's doing what we want it to do. It's always a good feeling. And we have essentially accomplished what we need to from this portion of the lab. And yeah, guys, I think feel free to let me know if you have any questions, or if maybe didn't go into a concept as well as I should have, or if I went way too much into a concept and you're like, hey, I already know this. I didn't get to go over select case, but it's just actually they asked us not to use this one in this lab, but it's another useful way of doing it. Maybe you can pause the video and take a look at it, but I'll go into this element in more detail later. So, okay, great. Well, everyone, take care. Have a good Saturday night, and we'll see you in the next video.